Hello everyone, welcome back to Atomic Ascent, your trusted platform for mastering chemistry with a strong focus on all that enters exams. If you are aiming to build solid concepts and confidently solve all the questions based on chemistry, then you are in right place. So take out your notebooks, stay focused, and let's start building your chemistry foundation together. Let's get started. In the earlier video, we have actually done about the mass percentage. We are actually doing the concentrations. Okay, so we have already done the mass percent. Okay, now we are going to do today parts per million and other one, which is molarity, molality, and normality. There is another one which is known as formality. We'll touch a few uh, basics of that formality one. Okay, let's start with parts per million. So as the name suggests, we are actually going to focus on the parts. We are talking about concentration, so concentration is always based on the solute. So parts are of solute parts per million mean 10 raised to power 6. Okay, so as you can see, this is a very big amount. This is going to be solution. Okay, so this particular solution has a very large amount, and solute in comparison is going to be very extremely small. Okay, so when there is a very small or extremely small amount of a particular solute, and we have to measure that concentration, then we are going to use parts per million. Okay, for example, if you have been told that in a particular given sample of water, what is the concentration of oxygen, or you can say what is the concentration of nitrates. Okay, so for those very small amounts, we are going to use parts per million as concentration term. Okay, so what is going to be the formula for parts per million? Suppose there are two components, component A and component B. Okay, this can be anything, and you have to you are mixing that, okay, and making a solution. You have to measure the parts per million of component A, okay, which is also known as ppm. So parts per million of component A is equal to, okay, mass of component A divided by total mass of solution, whatever solution you have been given, multiplied by 10 raised to power 6. Okay, this becomes parts per million. Let's take an example. You have been given a water sample, okay, and its volume is, suppose its mass or volume, anything is given. Suppose its volume is given 1 liter. 1 liter means 1000 milliliter. Okay, and it is also given that the density of the water is, suppose density is 1 gram per milliliter. So the mass of water sample is going to be uh, density into volume. And density is 1 gram per milliliter multiplied by 1000 milliliter. Milliliter cancels sounds and it becomes 1000 gram. Okay. And in this water sample, mass of chlorine has been given. That is 3 into 10 raised to power minus 3 grams. Suppose this much has been given. Okay. Calculate the concentration of this given sample in parts per million. So parts per million for chlorine is going to be uh, mass of chlorine, which is 3.3 into 10 raised to power negative 3 grams, divided by mass of water sample is actually solution. Okay. Obviously, this is a water sample. This is not a pure water. So obviously, it is a solution, that is 1000 grams. And we have to convert it into parts per million multiplied by 10 raised to power 6. Gram and gram cancel. Okay. And this will go above and it becomes 3 into 10 raised to power minus 3 into 10 raised to power minus 3 multiplied by 10 raised to power 10 raised to power 6. And this is cancelled down everything and it becomes 3 parts per million. So the water sample has how much chlorine? 3 parts per million, 3 ppm. Next one is molarity. Okay, this is the amount of solute, or you can say number of moles of solute in 1 liter of solution. Okay, so that is molarity. If I say that molarity, which has a symbol capital M, is equal to, what is that? Number of moles of solute divided by volume of solution in liters. Okay, but most of the time when we do these kind of calculate the molarity, the volume is never taken in liters because liter is a very big term. So what we do, we can use it in the milliliters. In that case, we have to convert liter into milliliters. Okay, so what we are going to do in that particular case, molarity, which is capital M, is going to be number of moles of solute divided by volume in milliliters. We are talking about volume of solution multiplied by 10,000. Okay, so this is what we have done over here. And if you have been asked that what is the unit of molarity, so we can put the units of number of moles and volume, obviously, uh, because this milliliter has been converted into liters, so obviously it is going to be in liters. Number of moles has mole divided by liter, mole per liter, or it can be written as mole liter inverse. Okay, this is one. And once more, this mole liter inverse is also known as molar. Okay, so what we do, we give it a symbol capital M. Okay, let's take an example. Suppose you have been given a question. Let's take a question over here. Suppose you have been given solute. This is a question. Okay, I'm making this question. Solute is sodium hydroxide. Okay, and its mass has been given, that is 2.46 grams. Okay, Molar mass, we know about that. What is the molar mass of sodium hydroxide? It is 40 grams per mole. Okay. And this has been taken in a solution. And the solution, volume of solution is 100 centimeter cube or cubic centimeters. We know that 1 cubic centimeter is equal to milliliter. So it's milliliter. You can convert this milliliter directly into liters, or you can use this formula of molarity over here. So first we need to find out the number of moles of solute. Solute over here is sodium hydroxide. So number of moles of sodium hydroxide is going to be given mass of sodium hydroxide divided by its molar mass. Okay, so given mass is equal to 2.46 and divided by 40, and we can calculate it. 1.23 it becomes, and then it becomes 0.123 divided by 2, and then I have to cancel it. 0.6, take it 0.6, and it becomes 1, it becomes 5, it becomes 0.0615. All right, it is number of moles. These are moles, obviously. Okay, so calculate the molarity of the solution, sodium hydroxide solution, that is number of moles divided by volume. If it is in milliliters, then multiplied by 1000. 0.0615 divided by volume was 100 into 1000. Okay, 0 and 0 cancelled. 0 is multiplied over here. It becomes 0.615 moles liter inverse, or you can directly write it down molar. So this is how the molarity is calculated. Our next concentration term is molality. Okay, its symbol is a small m. Okay, what is molality? Molality is actually uh, amount of solute in 1 kilogram of solvent. Okay, so molality small m is equal to number of moles of solute divided by mass of solvent. We are talking about solvent over here, not solution, in kilograms. Most of the times, once again, because kilogram is a big term, we don't take it in kilograms and we have to convert it into grams. So it becomes number of moles divided by mass of solvent in grams multiplied by 1000. And when we talk about the unit of molality, okay, so it is number of moles divided by mass in kilograms. So obviously number of moles are going to be moles divided by kilogram, which is mole kilogram per kilogram, or it is mole kilogram inverse, or this is also written as molal. It has a symbol of small m. Okay, so this is how it is written. And let's see one question. Okay, once again we are going to do one question. Suppose you have been taken a solute, uh, potassium carbonate is taken, whose molar mass is, you can calculate the molar mass if it is not given, but it's is 138 grams. And its mass in the solution have been given. Potassium carbonate's mass have been given. It is suppose 20.7 grams. I'm just taking any other. Okay. Then what we have done is we have taken the volume of water. Water is solvent over here. So volume of solvent is given 500 milliliter. Now the thing is, you have been given volume and you have been told that you have to calculate the molality. Okay. So you have to calculate the molality. Now, you know that in the formula of molality, there is no volume. Okay. You need mass. So once again, we will assume that this solution, this solvent water has a density of 1 grams per milliliter. Okay. And then we have to convert volume into mass. So density is equal to mass upon volume, and mass is equal to density into volume. So density is 1 gram per milliliter multiplied by 500 milliliter is the volume. Milliliter and milliliter cancels, and it becomes 500 grams. So the mass of water becomes, water is solvent, we have calculated for that 500 grams. Okay. Now we know the mass of water. Okay. We know the given mass of potassium carbonate and molar mass of potassium carbonate. We can calculate the number of moles of potassium carbonate. That becomes 20.7 divided by 138 directly. Okay. And it becomes 0.15. It is number of moles, so obviously unit should be written over here. Then the molality small m becomes number of moles of potassium carbonate divided by mass of water in grams multiplied by 1000, because what we have got is the mass in grams. Okay. So number of mole is 0.15 divided by 500 multiplied by 1000. Two zeros are cancelled down and becomes 2, and it becomes 0.30 molal. So this is how the molality of a particular solution should be calculated. Let's talk about the difference between molality and molarity. Okay. First point of difference is that in molality, we take mass of solvent in context, and over here we take a volume of solution. Its symbol is capital M. Its symbol is small m. Okay. Its unit is moles per kilogram. Its unit is moles per liter or molar. Over here it is molal. Okay. One more thing you have to remember, because molality depends upon mass of solvent and molarity depends upon volume of solution. You should know that volume changes with temperature. Okay, if the volume changes with temperature, then molarity should also change. Molarity changes with temperature. So if temperature increases or decreases, the molarity also changes. Now you should also know that how does it change. As we know that molarity is inversely proportional to volume, we should see that what is the relationship of volume with temperature. If the temperature increases, volume increases. If the temperature decreases, volume decreases. Okay, so temperature and volume are directly proportional to each other. If that is the case, molarity is also inversely proportional to temperature. So if temperature increases, molarity decreases. If temperature decreases, molarity increases. So there is a relationship between molarity and temperature. Whereas in case of molality, mass is independent of uh, temperature. So even if the temperature increases, decreases, molality does not change. Okay, molality remains the same. So if I ask you that which one is preferred, which one is better, so obviously it is obvious from this that molality remains the same in all type of temperature conditions. So molality is better. Okay, it and molarity is not should not be chosen in any case. So molality becomes better. Okay, so this was difference between molality and molarity. Next concentration term is normality. Normality, whose symbol is capital N, is actually number of gram equivalents of solute dissolved in 1 liter of solution or volume of solution. Okay, so normality is equal to number of gram equivalent of solute divided by volume of solution in liters. Once again, it is equal to number of gram equivalents of solute divided by volume of solution in milliliters. Suppose the volume is taken in milliliters, then it should be multiplied by 1000. Now the question arises that we are talking about gram equivalent of solute. What is this gram equivalent of solute? Okay, and how is it calculated? Before doing that, let's know about the unit of normality. Unit of normality is number of gram equivalents. So gram equivalent divided by volume was taken in liters. So liters, it's equivalent liter inverse or gram equivalent per liter. And once more, it is also written as normal solution and its symbol is capital N. So we were talking about number of gram equivalents of solute. How we are going to calculate it? It's mass of solute divided by equivalent mass. Now, this is how it is not easily cleared. So, let's take a few examples and calculate number of gram equivalents of that solute. So, mass of solute is going to be the given mass. Mass of solute is going to be the given mass. Okay. And equivalent mass has to be calculated. So, equivalent mass is calculated. It is uh, molar mass divided by n factor. Now, what is this n? Suppose we have an acid. Okay. For an acid, number of replaceable H positive ions are going to be n. Okay. Which is known as basicity. Okay. And for a base, okay, number of replaceable OH negative ions is going to be that n factor, and over here it is going to be called acidity. All right. So suppose you have been given uh, any acid. Let's take oxalic acid, and it is going to be H2C2O4 2H2O. Okay. Suppose this oxalic has acid and its molar mass is equal to 126 grams per mole. And suppose its given mass is um, 31.5 gram, and volume of solution is given. Suppose you have been taken 500 milliliter, and you have to calculate the normality for that. Okay. First, we have to calculate equivalent mass, that is molar mass divided by, because this is an acid, so basicity. Molar mass is 126 grams per mole, and basicity over here is, there are two replaceable hydrogen ions, so 2. It is going to be 63. So number of gram equivalent of uh, oxalic acid is mass given, which is 31.5 divided by 63. It becomes a 0.5 gram equivalents. Okay. So the normality is equal to that gram equivalents 0.5 divided by volume, that is 500, but it is in milliliters, so obviously multiplied by 1000, and it becomes 1 gram equivalent per liter, or directly one normal solution. So this is how normality is calculated. Our next one is formality. It is very rarely used but can be used sometimes. Formality has a symbol capital F. Formality comes from formula mass unit. And in class uh, ninth, you have done about the formula mass unit. So that formula mass unit of uh, an ionic compound present in 1 liter of solution. Once again, this is very simple, and we are talking about number of formula mass units. Okay, so formality is equal to number of formula mass of a solute divided by volume in liters. Volume of solution we are talking about. And if it is not given in liters, then obviously in milliliters multiplied by 1000. So this was very simple. For there is one term also that is called mole fraction. Okay, mole fraction has a symbol X. So as we know that a solution is made up of two components, is at least component A, component B. So suppose I have to know about the ratio of component A amount to the total amount. So that is mole fraction. It is actually ratio of number of moles of one component and total number of moles. Okay, when we are talking about total number of moles, we are talking about the number of moles of a solution. Okay, suppose we have to calculate the mole fraction of component A. XA is equal to number of moles of A divided by total number of moles. Suppose there are two components, so Na plus Nb, and if there are more components, then so on. So this is how it is calculated. For second one, we can calculate Nb is equal to Xb is equal to Nb divided by Na plus Nb, and if there are more components, then they are added as such. One more thing, when we add mole fractions of both the components of a binary solution, its answer is going to come 1. So if one component mole fraction is calculated, then 1 minus xb can be done. And if xb has to be calculated, xa we have calculated already, then 1 minus xa. Okay, so this is how the mole fraction. So these are the different concentration terms which are used in whenever we are talking about the reactions occurring in the solutions. Solution can be aqueous, non-aqueous, anything. And that brings us to the end of today's chemistry session. I hope you have learned a lot from understanding the concepts to how clearly calculate and solve the questions based on the concentrations of the chemical reactions. So thank you so much for watching. Keep learning, keep practicing, and keep ascending. See you in the next video.